Alrighty. So we might have some other people kind of joining in the next minute or so. Can everyone hear me? Okay. So what we're going to do today, I know that many of us are kind of preparing for our chapter math counts contest, which quite likely, depending on which chapter you're in or which state you're in, could be like about 2 weeks from now, right? So I know people taking it at K-State. There's two of the chapters from Kansas that are going to be taking it at K-State's Manhattan campus. So for when it comes to the individual component of the math counts test, there's a sprint round, which is 30 questions, no calculators, and we're going to do one of those next week. And the other component of the individual round is this target round. So a target round, you get 8 problems. They give you two of them at a time, right? You can use calculators on this particular round. And this pair of problems that you get 6 minutes to complete them. And one thing to kind of note here is if you get them done, you can't go to the next round. If you're like, say, oh, I messed up on the last two problems, you can't get it back. And in large part, why do they do this? A lot of times at chapter rounds, it takes a while to grade these things, right? Because you write your answers on the side. And so some people are actually going through and grading this, and they need to get the results pretty quickly so they can figure out who's going to be in the countdown round. And so this is a way that as they're kind of working on the sprint round, they can get two problems to grade quickly at a time. And, instead of just having an 8 question test that, they give you like a certain amount of time for. So one thing to kind of note with the target round, this isn't always the case, but oftentimes when they give you a pair of problems, there's going to be one which is kind of more doable and then one that's kind of harder. So there might be one that's a little bit faster and one that's going to be taking more time. And largely, like the harder problems are going to be used to differentiate people who are kind of coming in, like if they're trying to figure out who's going to be in the countdown round, who's going to be in what place in the countdown round, stuff like this. That's where some of these like kind of harder problems come in. And I know that they can be a little bit frustrating for students because, this is not like, maybe your math quizzes or tests that you take at school where you want to get your 90% or your 80% or whatever. Sometimes these are actually pretty hard tests. And so what I've picked out here is a pretty hard year, in my opinion, with respect to the chapter test. So what we're going to do is I'm going to give you 6 minutes to work on each of these 4 pairs of problems, and then I'm going to go through the solutions. So, but you kind of get a little bit of the feel of the real contest. So I'm just going to give you 6 uninterrupted minutes in order to try to work on this. So we're going to focus on the first 2 problems now, and I'm going to start the clock. Okay, so during the actual competition, during the 6 minutes, they might have a timer on the board depending on who's proctoring it, and they might do announcements like 1 minute left, 30 seconds left, or something like this. But that might not be consistent from center to center exactly what they do, but usually they announce what announcements that they're going to make before the round starts. So I saw a lot of correct answers for number one. So here we're bumping up the price of each of these oranges from 69 cents to 49 cents, or from 49 cents to 69 cents. So each one of these oranges is going up 20 cents in price. There's 6 of them. So 6 times zero point 0.2 is going to give you 1.2. But note that because we're talking about dollars, you're going to want to put 1.20 here. So they have kind of like really detailed math counts rules. And similarly, if they ask you for in simplified fraction form or in decimal form or something like that, just make sure that you answer it the way that they're asking. And if anyone has any questions, we can kind of go back to problems. The problems are definitely going to increase in difficulty throughout this round. I find some of the later questions here are pretty hard for chapter round problems, in my opinion. So, all right, so this next one, there are kind of fun-filled tools that you might have or formulas that you might have memorized. And so MathCounts technically is allowed to ask Algebra 1 questions. If anyone here has not taken Algebra 1, this is a problem you might not really know how to attack, and that's totally okay. Might make a little bit more sense next year. So when we look at this, we got this line y is equal to 3x plus 7. Maybe it looks something like this. Doesn't matter too much. But just to kind of get a sense of what we're looking at something which is going to go through quadrant, what we're looking at for this x and y intersect, these things are going to be over here. So when we're kind of playing around with this, we can find the y-intercept pretty quickly for those of us who've had Algebra 1. This is just going to be this number here, 7. So the y-intercept here is going to be 7. And the x-intercept, well, there's some handy-dandy formulas you could have kind of relating it to these numbers 3 and 7. But if you don't really remember those things, it's equally good to just say it's that, well, this is going to be where the y value is 0. So this is going to be where 0 is equal to 3x plus 7. You can subtract 7 from both sides. What you do to the left, you do to the right. And you'd find that the x-intercept is going to be at negative 7/3. That means that this new line is going to have x and y intercepts, which are going to be double these two values. Okay, time would be up. So let's see how we could do these two problems. So problem 3, let's just kind of go through it in two ways. One's a little bit more straightforward. One might be a little bit faster. And again, you can use a calculator on this. So I'm going to work this without a calculator, but you certainly could use a calculator on this and that would be faster. So, and one thing to note is just like make sure you have a calculator you're comfortable using. And sometimes like the fanciest calculator on earth your older sibling might have that you don't know how to use or turn on isn't always the best calculator. So something that you might be using at school, and oftentimes your MathCount coach quite likely is bringing, whatever calculators they use in school, but not always. You might want to double check. So we got these two teams, the cubes and the bisectors. And so the overall games are going to be 40 minutes, right? So we have a 40-minute game, and then we're effectively given a rate that they're scoring. So the cubes are scoring 21 points in the first 12 minutes. And so this is going to tell you if they kind of kept scoring at that rate, how much they would score the entire game. So you can kind of simplify fractions. But again, with a calculator, you could do 40 times 21 divided by 12, and boom, there's your answer. I could divide in a 4 here and here. Kind of simplify this to 10 times 21 over 3. I could divide in a 3 into the 21. That would give me a 10 times 7, or I get 70. But again, with a calculator, 40 times 21 divided by 12, I would get this 70 points very quickly. Again, you might simplify things a little differently than I am. Bisector scored 18 points in this 12-minute time period. And again, to simplify this, I might, if I didn't have a calculator, I might say 18 over 12 is the same thing as 3 halves. Could divide the 2 into the 40. I have a 20 times a 3 or a 60. But again, a calculator probably is going to be faster at this stage. But again, if you have time at the end, double check that you didn't mistype things, and always use your time on these tests. This is the most important rule of test taking that I tell students in college all the time. If you have 30 minutes left on a test or 2 minutes left on a test, check your answers, go through things, make sure you answer the question that was asked. That's really important in math counts because you can do all the right work, but you like say, well, okay, I'm figuring out what A and B are, and then they ask you for B, and then you write down A, you're not going to get points on that. So just double check that. That's something, that is very important. So we can see here the cube scores 70, the bisector scores 60. There is a 10-point difference between their scores. So that works. Alternatively, like something maybe a little bit more clever, in this 12 minutes, section of the game, the cubes score more than the bisectors. So the cubes score 21, the bisectors score 18. So the cubes score 3 points more than the bisectors. And so you could also do kind of the rate. There's 40 minutes and the cubes are scoring more than the bisectors at a rate of 3 points in every 12 minutes. We could simplify this fraction and also get at 10. That might be a little bit faster. But to be totally honest, though, if you have calculators, sometimes doing the fancier thing is more prone to like having an error in your work. So it might not always be the best thing, especially if you can use a calculator. These calculations are pretty quick on a calculator, and you might be able to do this very quickly and then reserve a lot of time as you tackle, which in my opinion is the harder of the two problems on this, which is number 4. So if anyone has any questions, we can roll back to number 3, but otherwise I'm going to work through number 4. This is one of these questions about kind of angle chasing, which you may have seen a lot of. You may have never really worked a lot with this stuff. So some kind of key points to note here is if you look at these angles inside of a triangle, they're going to add up to 180 degrees. If you look at the angles inside of a quadrilateral, they're going to add up to 360 degrees. So they give us some information here. Namely, they give us the angle DAB was 84 degrees. And they give us that the measure of angle ABC is 32 degrees. Now notice that we have nice symmetry here. So that is also kind of telling us this angle D is 32 degrees. But because we have these are going to bisect the angles. So these line segments here are going to split these angles in half. So if I want to just figure out what, like, say, 1/2 of this thing is, well, two of these things together are 32 degrees. So one of them is going to be 16 degrees. So each one of these things here is going to be 16 degrees. Now, that doesn't necessarily seem all that helpful from the get-go because it asks us what is the degree measurement of the acute angle where the dashed line segments intersect. So like what we're actually trying to find is this, or is this particular angle here. So these two angles are the same. So you could find either one because that's the acute one. This one here would be the obtuse one. So it's not totally clear how to directly get this. So, but I happen to know that if I add up the degrees of all the three angles inside of a triangle, they're going to add up to 180 degrees. So that would enable me to figure out, for instance, what this angle here is. Because if I think about this angle here, whatever it is, plus 84 degrees, plus 16 degrees needs to add up to 180 degrees. So I could figure out what this is. This is going to be 180 degrees, the sum of all three angles inside of a triangle, minus the two that I know, minus this 84 degrees, and minus this 16 degrees. So effectively, I have 180 degrees minus 100 degrees. And again, you could use calculators here, and maybe don't even need to simplify here until the last step, but we could find that this particular angle is 80 degrees. And we have symmetry here, so this angle over here is also 80 degrees. Now, this angle here, I don't necessarily know how to find yet. So, but I can figure out what this angle here is. So if I want to figure out what that angle is, and again, there's probably other ways to do this. This is just how I did it when I first looked at this. I know that if I add up these interior angles of a quadrilateral, they're going to add up to 360 because basically I could chop it into two triangles, each that have 180 degrees. So this angle here, if I add up all three of them, they need to be 360 degrees. So whatever this thing is, plus these other three need to add up to 360 degrees. So what I do is I subtract off the 80 degrees, I subtract off the other 80 degrees, and I subtract off the 84 degrees. And, maybe a calculator is your friend at this particular point, depending on how you feel about mental arithmetic. But this is 360 minus 244. And so this angle here is 116 degrees. Now, we did find one of the two angles here where these dotted lines are going to intersect, but they ask us specifically for the acute angle. Note that 116 is over 90. So what I actually want to find is this angle here. But note, if I add up this angle plus 116, they make for a straight line. And so you're going to have 180 degrees. So similarly, this angle, this orange angle plus this red angle need to add up to 180. So 180 degrees minus 116 is going to leave us with 64 degrees. Now, this is not the only way you could have worked this particular problem. So if you did it some other way and got the same answer, that's cool. I saw some correct answers in the chat. But this, I think we can agree, is a harder problem than three. I mean, oftentimes when they give you these sets, they kind of mean for one of these problems to be kind of more doable, and one of these things are probably something that a lot of people are actually probably going to get wrong on the test, but it might help them figure out who's kind of, in the higher rankings for the countdown round. If anyone has any questions, you put it in your chat, raise your hand. Otherwise, we can kind of do problems 5 and 6. And note here, the difficulty is going to start ramping up a little bit. So usually, especially questions 7, 8 are usually pretty difficult on these target rounds, especially question 8. Okay, well, I'll reset the timer and let's look at 2 new problems. All right, that would be time. And note here, I mean, questions 6, 7, and 8 on this test are pretty challenging. I didn't see a lot of correct answers for 6. I saw a lot more answers for 5. 5 here is kind of like one of these problems where maybe they kind of give you a little too much information and you start doing kind of fancy things. If you kind of look at it though, so one of the things that can make hard geometry problems easy sometimes if you magically add into the diagram some stuff that just kind of simplifies your work. So what we could do here, it's not obvious to do this, and that's what makes this problem hard, but after you do this, it's not nearly as bad. If I just draw here, from the center of this square, I kind of draw, 2 lines. I kind of chop up this big square, and I kind of have a quarter of the square here. Now, if you look at this, we got this region here that's shaded in. We got this triangle that's shaded in. We have this triangle here that's not shaded in. And you might, if you don't really have time and you want to guess, it might be like reasonable to even guess, oh, that triangle looks pretty much the same thing as this other triangle. But we can actually see that that's going to be this actually true here. So for instance, if I say that this angle is theta here, note, these are right triangles. So if that angle is theta, that would mean that this angle here is 90 minus theta, right? But note here, this other angle, if we are looking at the square here, this is a 90-degree angle as well. So that's going to force this thing here to be theta. So if we're kind of looking at these triangles actually have, for those of us who've had a little geometry, we have angle, side, angle, congruence. I mean, you can see here that all 3 of these angles need to be the same, and we have one of these side lengths are going to match up. So you find here that this triangle looks like this is going to be the same thing with a little rotation to this triangle over here. And so if you kind of take this triangle and you were to dump it in over here, what you see here is you're just filling in a quarter of this square PQRS. So the shaded area is equal to 1/4 of the area of PQRS. So this is one that I feel like they gave you a lot of information, and if you try to put some of that information like, oh, here's this side length and this other thing is going to be 3x or something like that, it can make the problem actually a little bit harder. But sometimes that's how things work in the real world. I mean, when you solve a problem, you have tons of information and only 3 facts are actually going to be useful. Question 6 here is, 6, 7, and 8 here were pretty challenging when I was just kind of picking a year to do, with respect to, chapter contests anyway. So here, we got to kind of figure out what's going to happen when we square these numbers. So if I have some number, say yx, and I'm just going to have y and x denote the digits. So these are some number between, 0 and 9. And I square it. I mean, this would be the same thing as having a 10y plus x squared, or 100y squared plus 20 xy plus x squared. So we have 2 numbers that kind of look like this. But we know that the units digit is going to be the same in both of these. Ah. So we could do this. We have two numbers that look like this. So they have the same units digit, but the tens digit is going to be different. And somehow when I look at the difference of these things, I'm getting this rather large number, 2340. So I could do this, and let's just suppose that my y is bigger than z, so that when I subtract these things, I'm going to get this difference. So when I subtract these things, we get that the difference between the two resulting numbers is 2340. And this is going to be the same thing as the difference between these things when I have them expanded out. Note here that the x squared and the x squared would cancel out if I'm subtracting. So when I cancel that out, what do I really have? I have 100 y squared minus 100 z squared. So I have 100 y squared minus z squared. What else do I have here? I have 20 times xy. Sorry, this is uh, I have xy here. This should be xz here. So xy minus x. And then these x squared minus x squared would cancel out. So the difference between the two squares was 2340. And then when I'm kind of the difference between 100 times the tens digit squared, 100 times the tens digit squared would be this. And then we also have these 20xy and 20xz when I expand that out. So this is not obvious necessarily yet how to work with this. So what you might want to do is just kind of factor stuff out as good as you can. So for instance, this thing here is a difference of squares. So y squared minus z squared is the same thing as y minus z times y plus z. And you could also factor y minus z out of the second creature as well. And I guess you're also going to have an x. Or we could just factor an x out and see that we have an x times y minus c. So when I look at everything I have on this right-hand side, well, okay, so I have a 20 as a number, so I'm going to factor a 20 out of both of them. And I also have a y minus z. So let's factor a y minus z out of both of these expressions I have on the right-hand side. What would I be left with? Well, okay, so I took 20 out of this 100, so I still have a factor of 5. And I have this factor y plus c. From here, I still have this factor of x. Now, this here is not necessarily super fun to deal with if you don't have a calculator. So one thing you might want to do is let's at least simplify the numbers that I have. I'm going to divide both sides by 20. That might not be the easiest thing to do if you don't have a calculator, but if you have a calculator, you could factor this is going to be 117. Or sorry, if I divide 20 by this 2340 divided by 20, I get 117. Again, you could, if you don't have a calculator, you could kind of kill off the zeros and then divide 234 by 2. So this would be the same thing as y minus z times 5y plus z plus x. So at this point, this is looking pretty awful. But one thing we note here is I have two numbers, two expressions here that are getting multiplied on the right-hand side. And we have this fundamental theorem of arithmetic that when you have a number, it only can be factored, in one way up to the rearrangements when I'm kind of factoring the natural numbers. So this is where you might want to factor this number 117. Some calculators will have a factor button. But one thing you could kind of note here is this thing is going to be divisible by 9 because 1 plus 1 plus 7 is going to be 9. That's divisible by 9. We kind of talked about divisibility tricks in the earlier part of last semester. So we can see we have this factor of 9 or 3 squared. And the other factor here is going to be 13 if you were to divide that number by 9. Okay, so what we see here is that what I have on the right here, this y minus z and this 5 times y plus z plus x, these two numbers need to kind of, there's going to be two threes and there's going to be 113 when I do this. So one thing I note here is y and z are going to be digits. These are some numbers between 0 and 9. So I'm going to have, well, and actually, these are two-digit positive numbers. So I actually know that y and z are going to be numbers between 1 and 9. So we can't have y minus z actually being 9. We definitely can't have it having a factor of 13. So my number here, this factor y minus z that I have, it needs to either be 1 or 3. So I can't have it be 9 because that would force that z was actually equal to 0, which means that this number here wouldn't have been a two-digit number to begin with. Um, okay, so but let's suppose for a second that this was 1. If y minus z was 1, that means that all of this 117 are coming from this factor over here on the right. But we can actually bound that. I mean, the biggest that this 5 times y plus z plus x could have been is, well, I could have like y be 9. Y and z aren't the same, so I could have z be like 8. And I could have x be 9. But if you actually plug this into a calculator, the biggest that this factor here could be is 94. So there's no way that I can have y minus z equaling 1 because then all of that 117 need to be living inside this other factor, and that can't happen. So what this tells us is that my y minus z here has to be equal to 1. Okay. You're sorry, is equal to 3. Sorry. Y minus z needs to be equal to 3 because if this was equal to 1, we would have a problem. Okay, so now they know that y minus z is equal to 3. I could, divide both sides by 3 here, and I'd find that on the right-hand side, I get 39. So 39 would be the same thing as this 5 times y plus z plus x. And I just want to note here, this one is hard, and the remaining 3 ones we have are kind of difficult. So like, there's kind of a lot of pieces here, and we're using some tricks, and this is not just a 3-line problem. This is actually pretty long. You might be able to guess and check an answer too. If you don't really know how to deal with a problem like this, but you have time, and kind of play around to see if you can kind of make something work, and you might be able to figure something out. So if you look at this equation here, 39 is equal to 5 times y plus z. This factor here is going to be a multiple of 5, right? So I need to hit 39, but this thing here is a multiple of 5. So I'm just considering this expression mod 5. We know that x is equal to 4 or 9. Because we know that we need to add a multiple of 5 plus x. X is going to be some number between 0 and 9, and I need to be able to get 39 from it. Okay, so one of these two things is going to be true. But if x is equal to 9, you can actually figure out what y plus z needs to be. So that would say that y plus z would be equal to 6. If x is equal to 4, so that would say that 5 times y plus z needs to be equal to 35. So your y plus z needs to be equal to 7. So one of these two cases is going to happen. But what happens when we do this particular case? Well, I know that y minus z is equal to 3. I know that y plus z is equal to 6. If I add the two equations that I have in gray here, that would say that 2y is equal to 6 plus 3, which is 9. And that can't happen because y needs to be an integer. So we know that's not the case. We know that we must be dealing with this particular case here. And again, we could actually figure out what this is. So x would be 4. If I take this equation here and I add it to this expression up here, I would find that my 2y now is equal to 10. So that's going to tell me that my y is equal to 5. And that would tell me that my z is equal to my y minus z needs to be 3, so my z is equal to 2. And now I have everything I need. So if I'm thinking about this, my yx is equal to 5, 4. My zx is equal to 2, 4. And when I add these two numbers together, I end up getting 78. So, which, I mean, I saw a couple correct answers in the chat, but I mean, this is, in my opinion, a very hard question 6 for for a chapter level contest. For the state level contest, this is, totally and utterly reasonable. But, so one of the reasons I chose this one though is just so we kind of do a harder year before we kind of go into the real contest in 2 weeks. I'm not sure if anyone has any questions, and I realize some of us might have been lost in the middle of it because I was using number theory. I was using a lot of algebra in the process, and some of us might not be comfortable with some of the stuff that we use. Yes, go ahead. Is there a question? You can pop your mic on or toss in the chat. Do we bring our own calculators for the actual contest? So this is something that you probably need to ask your MathCounts coach. So at the contest center, the people proctoring aren't going to have calculators for you. Your coach might bring calculators, but they might not. So this is just something to kind of ask them, because if they're not bringing it, then see if you have a calculator at home or can borrow one from a friend, a sibling, whatever. But the biggest thing is like it's a calculator you know how to use, because like some of the like newer like fancier TI graphing calculators, if you've never used them before, like you need to make sure you know how to turn them on and kind of use the basic functions. Was there another question? I saw a hand raised. Okay. Okay, so let's do these final two, and then we can kind of go through them. That probably will we'll finish our 6 minutes roughly at the end of our session, but I'll stick around and do the two problems for anyone who wants to do them. These are kind of longer ones, kind of like 6. Okay, so we can go through these, and if anyone needs to go, it is 11 o'clock. And I just want to say, like, so one of the reasons why I picked this particular year, it's kind of similar to if you're training for a 1 mile race, you probably are going to be running, 1.1 miles or something like this. So this is a good year to kind of train, just so you're kind of doing something that is a hard year before we kind of go into the real contest. So let's go through these two particular problems. So these are, relatively tricky problems. I saw, I think, 3 correct answers for 7 and 2 correct answers for 8. So it was a trickier set. So with 7, what makes this hard is this blob here in the middle. So you can't just relate it to some, X choose Y or something like this, at least not directly. So what we need to kind of think about is either we're kind of coming this way and down, or we're coming this way and over. So it's not easy to kind of do all this in one go. At least I didn't see an easy way to do it in one go without kind of using like some fancier sledgehammers from combinatorics. So, but if I'm going to the right and then down, I know I need to go through one of these 2 points. But I'm never going to go through both of them. So if I go through D, I can't get back up to C. If I go through C, I can't get back over to D. And kind of similar down here, I see that if I label these like say E and F, if I'm going down and then over, I need to go through one of these 2 points, and I can't, if I go through F, I can't get back up to E. If I go to E, I can't get back over to F. So I can kind of see here that I'm going to go through one of these points. So what I'm going to do is I'm going to count the number of ways that I could do this and go through either C, D, E, or F. Now, of these 4 things, F is kind of the easiest. If I want to, going through, if I want to figure out the number of ways going through certain points, F is actually pretty easy, because if I think about F, I'm just going to go 6 down, or I'm going to go all down and then all right. So there is a total of one way of actually doing this. Namely, I can go down and then I can go over, right? Okay. So which is the next easiest point? Let's see this point C here. C is probably the next easiest point here because once you get to C, you're just going to go straight down, right? So, okay, so if I wanted to do C here, okay, so how could I get from A to C? So going from A to C, you have to go 1, 2, 3, 4, 5, 6. 6 ways of doing that. Or sorry, there's 6 steps. There's 6 moves, but only one of them is down. To get to C, I'm going to do a total of 6 moves where one of them is going to be down. That can be done. You can put that down move in any of the 6 positions. You could go here, 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 here. There's going to be 6 ways of doing that. Then after that, you're just going to go straight down. So then all down to B. So for thinking about this, there are 6 ways I could figure out where I'm going to go down as I go from A to C, because there's 6 moves of which one of them is going to be down. So there's a total of 6 ways of doing this. Okay, so let's see which is the easier one. The next easiest one would be E, and these are kind of increasing difficulty. So the more comfortable you are with some of these counting arguments, the more you probably just are going to systematically do this. But I'm just kind of ramping up some of the difficulty as we go through these counts. If I go through this point E here, well, this is very similar to that first part of C. If you look at it, there's 1, 2, 3, 4, 5 steps. So there's 5 moves. Yeah, and as someone's saying in the chat, there's 5 ways to do it. There's 5 moves of which one is down. So I could go down, 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 right, one right. There's 5 moves and one is to the right to get to E. So there's 5 ways of doing that. But then similarly, when I go to E to B, there's 1, 2, 3, 4, 5 steps of which one is down to B. So if you're kind of thinking about this, there's 5 ways because there's 5 steps to get to E of which one is, I can choose any of them that's going to be right. There's 5 ways to get to E and then 5 ways I can get to B. And these things are independent. So I'm asking, is the formula the same for all of them? In some sense, yes, if you have kind of, so if you could write this all in terms of a very general formula where the parameters of the formula is going to change because we're going to need to use that. We're going to need to use choose here for the number of ways we can kind of count these things, the number of combinations that we have. So here there'd be 5 ways to get to E and then 5 ways to get to B. They're independent, so there'd be 25 ways of doing this. For F, this is the one that, or sorry, D is the one that's probably more complicated. Because when I think about D, there's a little bit more options here because you could go down first and then over to the right a few times and then down again. There's 2 different down steps that we're going to have. So if I'm kind of tracking this, I have 1, 2, 3, 4, 5, 6 moves. But in those 6 moves, in any of the spots in those 6 moves, I can go down. I have to go down 2 times out of those 6 moves, right? So 2 are down in order to get to D. So there's 6 moves. I can put those 2 down moves anywhere in 6 positions. This is combinations. This is like a counting thing. This is C of 6, 2, right? So once I'm at D, I do from D to B, and any one of them can be right. There's 4 moves, 1 right to B. 6 choose 2, or the number where, or, 4 ways of doing. You might be able to do this without could set up a similar formula here where you can have like something choose something times something choose something every single time. Just when there's only one thing you're choosing, the formula kind of breaks down as a little bit simpler, so you don't necessarily maybe need to use the fancier stuff. So this would be 6 factorial times 4 factorial. Like not bring in factorials. But this would be 6 times 5 over 2. You could also think of this as spots amongst the 6 that I could pick, the 2 down steps, but then the order that, selection doesn't matter, so I'd be dividing by 2. So there's ways you could do this without using this fancier symbol that we learned maybe in September when we started MathCircle. So when we do this, we have 30 divided by 2 times 4. We have 15 times 4, or we get 60 ways. So by far the most complicated of these steps is going through D. And then they're asking how many ways can we do this? We got to add all these creatures up. So 1 plus 6 plus 25 plus 60. So there's 32 plus 60. We get 92 ways. So this was a trickier one, and this how I did this is not the only way to do it. You might have had some other argument. Maybe your argument was even more clever than mine. Mine is just kind of procedurally how I would do this if I was like teaching a combinatorics class of like, let's break it down into cases, and these need to split up this particular way. So I don't need to kind of overcount. So that one's pretty tricky. Depending on how much of some of these counting arguments you've seen, this might have been worse than 8 or vice versa. 8 is more algebra. So for 8, it's kind of a big mess, but you need to kind of break down the mess into digestible pieces. So we have these 6 numbers getting assigned to these 6 variables. There's 6 factorial, which, you might want to memorize some of these things, but if you don't remember factorial, it's 6 times 5 times 4 times 3 times 2 times 1. Your calculator, if it's one of the kind of fancy graphic calculators, might even have a factorial button. I'm not sure. It kind of depends on the model, but we'd see 720. There's 720 ways that I could actually assign these variables. But if I'm only concerned with ones where this expression here, this kind of ugly expression, is equal to 1, well, I'm plugging in integers into this. So these integers, notice I'm plugging, the variables are never going to like give me 0 for these factors, but I can't have them give me 2 or -2 or 3 or -3 here. So to get 1, I know that all of these things need to be plus or minus 1. At the very least, that doesn't guarantee it. I can still get -1 for the expression. So you need all of these factors, and by all, I'm talking about these like m minus a, t minus h, all factors are plus or minus 1. Okay, so it's not totally obvious how to proceed here until you realize that some of these letters show up in 2 of these factors. So for instance, when I look at E is showing up both in LE and in T minus E, right? So what this is saying is that both of these 2 factors need to be plus or minus 1. And when I'm thinking about numbers, these 1, 2, 3, 4, 5, 6, the only way one of these factors can be 1 or -1 is if these two letters, these 2 variables are going to be consecutive, right? So I could have a 4 minus 3 or a 3 minus 4, but I can't have a 5 minus 3 because a 5 minus 3 is going to produce a 2 factor, right? So I could see here that these things need to be in ordered. So T and E need to be consecutive numbers, and E and L need to be consecutive numbers. One's going to be less than it, one's going to be smaller than it. So we need to have, if I'm just kind of writing these things in order, we need to have this look like in order for consecutive. LET or TEL need to be consecutive numbers, right? Because L minus E and T minus E both need to be plus or minus 1. So if E is going to be 1 away from L and 1 away from T, the only way that that can happen is if E is going to be sandwiched between L and T when I'm doing this and trying to figure out the order here. Okay, that seems really helpful. But before I proceed and kind of do anything kind of fancy here, let's see if there's any other letter that's showing up multiple times. Um, so H doesn't appear to show up multiple times. But one thing we note here is T is showing up 2 times here. So I have a T minus H factor, and I also have a T minus E factor. So I need T minus H to be plus or minus 1. I need T minus E to be plus or minus 1. That means that these letters are going to be consecutive. And similarly, T is 1 bigger or smaller than H. T is 1 bigger, 1 smaller than E. So these things need to be consecutive. So I also know that I could have, I know my T is sandwiched between E and H. So it could be HTE or ETH are consecutive. But if you note here, there is a little bit of overlap here because you're seeing that E and T are involved. Like I have an ET here, I have a TE here, I have a TE here, and I have an ET here. So these things kind of need to pair up and actually tell me that four of these variables need to be consecutive. And so, we must have one of two things. Either we have that LETH, that's if I have LET and ETH happen. Because no, I can't have LET in order and HTE in order because I can't have T both bigger and smaller than E. You could have that, or you could have the reverse that I have TEL, and then that would need to match up with HT. So it's kind of like hotel. HTEL are consecutive. So one of these two things has to happen again because I need all of these factors to be plus or minus 1. So let's just kind of break down what I'd have if I kind of do one of these things. If I have LETH is numbers in order. So let's look at this blob of these three factors over here. T minus H, uh, L minus E, and T minus E. So if I'm multiplying these things, if T is less than H, uh, so if T is less than H, this would be -1. If L is less than E, this would be -1. And if T is bigger than E, this would be +1. So I'm going to get a +1 from this. And that tells me that my M minus A is equal to +1. Or my M is equal to A plus 1. So that tells me that, my A and M are consecutive. So I know that AM is consecutive and length is consecutive. So basically, I'm going to put my AM either before length or I'm dealing with length AM. So there's two different ways that I could do this. I'm going to see a very similar behavior if I look at this HTEL. So let's just look at these last three factors here. So if I'm doing this, I have T minus H, L minus E, T minus E. So here, T is bigger than H, so this is a +1 factor. L minus E, that's a +1 factor. And T minus E, well, T is less than E, so this is -1. And I'd find that this is equal to -1. But if I need the whole product to be -1, that's going to tell me that this M minus A factor needs to be -1 as well. So my M is equal to A minus 1, which is just saying that MA is consecutive. So you have MA is consecutive, you have hotel is consecutive. So either this is going to look like Ma hotel or hotel Ma. Those are the only two ways I could have that block of 4 being consecutive and that block of 2 being consecutive. So one of these two things is going to happen. So note here, I've went through all the possibilities. There's literally only 4 ways that I can actually do this and have that this polynomial is going to spit out a 1. So there's 4 ways to do it out of 720. So the probability is going to be 4 divided by 720. But note that they're asking you to write this as a fraction, so you want to simplify this. Again, your calculator might actually simplify your fractions depending on your on the calculator that you have. You could do this in 1 step and 2. You could take a 2 out of both and have a 360 and then take another 2, or maybe you can kind of take a 4 out of the downstairs, or maybe use your calculator. We get 1 divided by 180. So again, I think I just want to note here because sometimes when you do some of these harder years, people kind of worry a little bit. Like in my personal opinion, these last 3 questions in particular were kind of, a little bit on the brutal side for a chapter test. Also that question about messing up the tens digits, or I guess never mind, that was question 60. So yeah, so I think like the last 3 questions here were kind of on the hard side. So if you didn't get them, that's totally okay. And also like depending on what you've had, I know a lot of us aren't, say, in Algebra 1 yet. Some of these other questions, even like question 2, if you've not really done a lot of plotting of lines and stuff like this, you might not really know how to kind of work with that. And that's A-okay. And then maybe something that we worry about for future years. So that's what I have for you today. Tomorrow I'm going to do, or next week, we're going to just go through the 2019 sprint round. So we can kind of see the other main component of the individual test. So if you're doing your individual scoring at the contest, it's going to be your sprint score plus 2 times how many you get on the target round. So you can get up to 30 on the sprint. You can get up to 16 on the target, contributing to your overall score. If you're curious about team scores, some of us may be on our 4-person team for our school. What they do is they take your 4 scores, they add them together, they divide by 4, effectively figure out your average score for your team. But if you have less people than 4, it kind of hurts you because they are actually dividing by 4. And then they add on the team round. So the individual scores collectively probably do way heavier on your team score than the actual team round itself. So we didn't practice the team round because I know that not all of us are actually taking the team round. But if you want to do that, that's something to kind of strategize with your teammates. Like how do you want to break it down? Who's doing what problems? You don't want it to be just a free for all. Like you might find that some of your teammates are really good at geometry. Maybe they should just take the geometry ones. Maybe you pair up, 2 people take some of the problems, maybe do even or odds. Maybe you have one person start with 1 and others start from the back. There's a lot of different strategies for doing this that different teams use, but it really depends on kind of who your teammates are. And I just want to note, like if some of us aren't on the teams, at least in some of the chapters, they still kind of let you take the team round for fun, just so you get that experience. Because otherwise, you're just kind of sitting around. So I hope that your regions let you do it, whether or not you're on the team. But like whether or not you're on the team, you can still make the countdown round. You can still make your state contests because generally speaking, it's gonna be the top 2 teams from your region, and then which is the 4-person team, not the entire 12 or 14 people you might have going, or 8 or whatever you have for your school. But then also the top 4 people on the countdown rounds also will go to state. So I will be, if you're going to the K-State regional or chapter, I will be there quite likely. We might have some math activities there for you, depending on, I got to talk with the MathCounts director, so for the state. So in any case, I hope you have a wonderful weekend. If anyone has any questions, I'll stick around, but otherwise have a great day. I'll see you next week, and maybe I'll see you in 2 weeks at K-State. So. Yep. Have a good day. You too. You're welcome. Any other questions or?